In our next section, we're going to talk about the different routing variations over MPLS traffic engineering, look at the differences between static routing versus dynamic with either auto route or forwarding adjacencies, and then talk about what are some of the potential problems we can run into when we're doing dynamic routing and how the cost of the tunnel is taken into account when we look at the end-to-end traffic flow. Now, before we get into these routing specifics, I do want to show another variation of our previous example, where what I've done now is to change the core of the network from ISIS over to OSPF. So between routers 1, 2, and 3, and on XR 1, 2, and 3, we're now running OSPF area 0. So we're simply running it on every single interface, and then under the global routing process, we've set OSPF to run traffic engineering for area 0, and then we've specified the router ID as the loopback. So as compared to the previous example in ISIS, the rest of the configuration is exactly the same. Enable TE globally, enable TE at the link, enable RSVP at the link on every single box everywhere, and then at the head end of the tunnel, we're configuring the actual tunnel interface. The difference here now is that when we look at the show MPLS traffic engineering topology, the difference is that ISIS is no longer advertising the TE information. We're going to be advertising it through OSPF instead. And actually, I need to turn the ISIS process off on these boxes. So let me, let's go to global, and we'll say no router ISIS 1. And then we'll commit, that's for the XR boxes. Okay, these 3. And then if we look at, likewise, the show MPLS traffic engineering topology, we should see that now this is going to be advertised by OSPF. Okay, also from this output, it tells you what segments are running as OSPF network type broadcast and who is the designated router for that particular segment. In most cases, in the SP core, like we talked about in IGP, you would want to be running these interfaces as point-to-point. But the OSPF config is really going to be independent of TE. It's simply that the LSAs from regular OSPF are related to the opaque LSA, which is going to be for the TE advertisements. We can also see this if we look at the show MPLS, or no, show IP OSPF database. We'll see that we have the new link state advertisements, which are type 10. These are for the area LSA, so it's for intra-area traffic engineering. And if we look at the show MPLS, or excuse me, show IP OSPF database for the opaque area, and we'll say, like, let's look at our self-originated one. This shows us what are the different constraint details that we're actually advertising into the topology. So things like what is the admin metric, this is the traffic engineering metric of the link, what is the maximum bandwidth of the link, how much is actually reservable, what are the different priorities, and what are the affinity bits of the interface, which again is more commonly called the link color. Okay, and notice here there is a difference here between the admin metric and the IGB metric. IGB metric being the OSPF one. The TE metric we can set separately at the link level. Okay, but these variations we'll come back to later when we talk about the path calculation. Okay, so again, in terms of the routing over the tunnel, there's mainly going to be 3 main variations: static routing, dynamic routing, and then policy routing. Static routing, pretty straightforward, like we saw in the previous example. We just say IP route, whatever the destination is, and then point it directly to the local tunnel interface. Now, the disadvantage of this, though, is that other devices in the rest of the topology cannot use your local static route unless you advertise it into IGP. So we could take on router 1, redistribute the static route into OSPF, redistribute it into ISIS, then we would be advertising that as a destination. Other devices could use that likewise as a dynamic link. The other options, though, are to just automatically advertise it into IGP and install it in the routing table. This is what either the auto route announce or the auto route destination will do. The difference between them is that auto route announce is going to install the link as an IGP path. Auto route destination is going to install it as a static route. So you could think of this as kind of just a shortcut in the syntax, that you don't need to manually configure the static route towards the destination. It's going to automatically put it in there, hence the name, it's an auto route. So if we take a look at this from router 1's point of view, and let's look at our tunnel config, show run interface tunnel 0. Pretty straightforward config, so we're not specifying any constraints. We're just saying that if you know a shortest path to 3333, then set up the tunnel. Okay, once the tunnel is actually up, if we look at the show IP route for 3333, we're statically routing them out the tunnel. If we now show MPLS forwarding table for that particular destination, we should see that the, or actually here, why does this show, let's see, why does this show no labels? This is related to, let's say for, show MPLS forwarding table for the particular destination for 3333. So for some reason, this particular version doesn't show you everything when you look at the show MPLS forwarding table. This shows you just the LDP allocated labels, where in this case, I didn't enable LDP in addition to OSPF. So it basically shows that there's no labels listed. But if you either look at the CEF table or you look at the exact route, and then it does show you what the traffic engineering tunnel label is. So if we show IP CEF for 3333, it should say, and if we look at the CEF detail, it says that it is, it doesn't show it there either. It does show it when we look at the show MPLS forwarding table here and then the out label number. It just depends on what particular version you're looking at. Some versions of regular iOS will show this all in show MPLS forwarding table, same as what XR does. Otherwise, you need to look at the detail verification for that particular destination. But in any case, the point being here is that when we do a trace route, we can see that it is following a labeled path. Okay, so it's using the label that came from traffic engineering. Okay, so let's now make a change to this. Let's remove the static route. Show run pipe to include IP route. And if we revoke this from global config, and then look at the details for MPLS forwarding, so a forwarding table for that particular destination, should tell us that there's no label. Okay, reason why is that I'm not running LDP with OSPF, and we don't have the route pointing out the TE tunnel, so this is going to be regular unlabeled traffic. If we do a trace route to the destination, we still have reachability to it because underlying IGP routing is working. It's just that we're not going out an interface that's running MPLS. Now, if we think about this in conjunction with either layer 3 VPN or layer 2 VPN, this immediately is a red flag. Because when we're verifying the core of the network, you want to do a trace route between the PE loopbacks, and if it does not show a label switch path end to end, you know that you're not going to be able to tunnel either L3 VPN or L2 VPN over it. So in our case here with TE, we could, like I said, we could either do a static route or we could go to the tunnel interface and we'll say we want to do MPLS traffic engineering, or actually we say, I believe it's tunnel MPLS traffic engineering. So the syntax is kind of fragmented, where some of the options are under MPLS traffic engineering tunnels, and some of the options are under tunnel MPLS traffic engineering. In this case, we want to set an auto route. Okay, we could set auto route announce or auto route destination. Again, the difference between them being one is IGP, one is for static routing. So before we do this, let's look at the show IP route for 3333. Right now we have OSPF pointing us out the physical link. If we say that we're going to do an auto route announce, what should change here is that we're still going to install the route as OSPF, but the difference is that it's going to point out the tunnel interface. Okay, so move from the physical link now to the tunnel. This implies then that since the tunnel is running MPLS, it's a traffic engineering tunnel, it means that we're going to use a label when we actually go to forward the traffic in the data plane. So if we now do a trace to 3333, we're using label number 27, which if we go to router 2, who is that next hop, and look at the show MPLS forwarding table, we should see that from 1, not to 1, so from 1, this is the midpoint of the tunnel. And if we look at the show MPLS traffic engineering tunnels, and we'll say for the specific, let's say, not the destination, I would want to say based on the name. And the name in this case is it 1111? No, that's not the name. That is the source ID. There we go. Source ID 1111. Okay, so from router 1, this is the rest of the path that we're using to route. So again, it is kind of confusing because it doesn't show you the label value in the forwarding table, but if you look at the details there or just look at the trace route, it shows you what the out label value is going to be. So if we look from router 1's point of view and now look at the show IP route, this is going to look like just any other IGB route. If we show IP route OSPF, we see some of the routes are out are physical links, but in this case we have this route pointing out the TE tunnel. Now again though, this is assuming that you are running IGP. If for some reason you're doing static routing everywhere, then auto route is not going to work because it's for IGP, it's not for static. But the other option there, which is the auto route destination, is going to do pretty much the same thing. The difference being is that it installs it as a static route as opposed to a dynamic route. So auto route destination. This option is iOS specific. iOS XR doesn't support this. So it's more common that you'll see most examples will do auto route announce because it's just a shortcut saying that if I form the tunnel to 3333, it probably means I want to route to 3333 out that interface, so automatically install it as a local IGB route. Now we'll see though that this is different from what we call a forwarding adjacency, where a forwarding adjacency is when we actually advertise the link into the link state database. So as we say either under OSPF or under ISIS, that this is where we're actually forming an adjacency from router 1 to router 3, and the other devices can use this as a route in the topology. Okay, so what I mean by this is that if we looked at, let's say, we go to XR1. And let's say that from XR1's point of view, we have 3 possible ways that we could route to get to router 3. We have the, well, technically 4, because we have our 3 physical interfaces here, and then we have the TE tunnel. But for now, for the sake of argument, let's remove the TE tunnel from part of that path. So we'll go to interface tunnel TE0 and shut it down. Okay, if we now show IP route for 3333, we should see that we have the path going towards 211, which is going in this direction. Okay, we should actually have an ECMP here. So let's see what the other boxes are doing. Let's look at this on everybody. XR2 says I'm routing to router 2 to get there. Why would it not route directly to router 3? Let's show IP OSPF neighbors. We don't have an adjacency to router 3 directly, so it's probably missing IGP on this interface here. Okay, so from XR2, let's say show run router OSPF, and it looks like we have it enabled. Let's show IP interface brief. Port shutdown. Okay, so on that physical link, or in this case the logical link, let's bring it back up. If we show IP OSPF neighbors, we should in a minute form an adjacency with router 3, which we do. Okay, so now XR1 should have an ECMP to get there. So 2 equal cost paths. Okay, next, let's look at this from if we were to route through router 1. So right now from XR1's point of view, the reason that we're going this direction or that direction is that since all of the interfaces have an equal metric value, we're looking at simply the hop count. So we're going 1, 2 hops in this direction versus if we were to go 1, 2, 3 hops in this direction via router 1. Okay, let's also say that these interfaces are not the same cost values. Let's say that from XR1 going this direction and this direction, these interfaces have, let's say, a cost of 2, where the link going this direction has a cost of 1. So now we're going to have 2 plus 1, which is 3 total, 2 plus 1, 3 here, and then 1, 2, 3 in this direction. Okay, so we should see then we have an ECMP going both ways. So from XR1, we're going to say that on OSPF1, under area 0 on interfaces, gig 0000.1112, the cost is going to be 2. And then the same on the diagonal port 211. Cost is 2. Okay, so if we now look at the route for 3333, we should see 3 ECMPs. So now it's saying the total metric is 4 in each direction. So 3 hops to get there and then 1 additional hop for the actual loopback itself. Okay, so if we were to do a trace to this, what we should see is that for every packet that happens to go over towards router 1 is going to send that over the TE tunnel, and it's really going to depend on how XR1 is hashing the traffic to the destination. So let's say the source is 11, 11, 11, 11. And for right now, let me actually shut both of those ports down. Okay, so now we only have one path. We trace to 3333. This should go over to router 1. And then 1 is going to send it across the TE tunnel. Okay, so the point being here is that when anyone forwards the traffic towards router 1, since its route is pointing out the TE tunnel, it's using that as the intermediate hop in the middle. So even though in this case XR1 is not running MPLS with router 1, it's not to say that a tunnel cannot be used somewhere else in the network. We'll see a little bit later when we talk about L3 VPN, this is an important point because you can have nested tunnels. That I can have an LDB tunnel inside of my TE tunnel, where the TE tunnel, maybe that's doing fast rerouting for me, or it's doing fast reroute, node protection, or link protection, where you can have multiple labels that are combining on top of each other. Okay, next we're going to bring those two interfaces back. So let's roll back the config, last one change. Now XR1 is going to re-enable all of its interfaces. We should form OSPF adjacencies again, and if we look at now the show IP route for 3333, we now have 3 ECMPs. So we're only using MPLS now when we go in this direction, down towards router 1. But if we take a look from XR1's point of view and look at the OSPF database, let's show OSPF database, and let's look for the router LSA that's originated by router 1. Or in other words, how is router 1 describing its view of the shortest path tree? Where it says that it has 4 possible links. Okay, these 4 possible links are going to be its loopback, and then it's going to be each of these links that are adjacent to XR1 and 2, and then router 2 respectively. So with the default behavior where we're running network type broadcasts, it should say I have links to 3 different transit networks, which are going to my designated routers. Okay, so this is going towards XR2 to XR1 and then to router 2. And then it says the 4th link is my loopback. But notice what it is not describing here. It's not describing the TE tunnel. Even on router 1, if we were to say auto route announce, okay, well right now if we show run interface tunnel 0, we're saying auto route destination, which is putting that static route in. If we were to go back to the tunnel and say we're going to run auto route announce, not auto route destination, and then we show IP route for 3333, we should install this as an OSPF route out the tunnel. And if we look from XR1's point of view and show router 1's database, it still says that it's describing 4 links. So in other words, even though the route is installed from OSPF's point of view, router 1 doesn't advertise this as part of the database to the other neighbors. This means when XR1 performs its shortest path first calculation, it doesn't see that router 1 has a direct tunnel over towards router 3.